Today on Macaulay Math, we're talking limits at infinity and horizontal asymptotes. Intro. Okay, good day. I'm Professor Macaulay. This is Math 200, Calculus 1, Lesson 17 on limits at infinity. Our goals for today. We will determine limits at infinity, and we will determine the horizontal asymptotes of the graph of a function if it exists. Limits at infinity and horizontal asymptotes are related in that they both explore what certain functions do as the independent variable grows without bound. In many cases, when we let the independent variable grow without bound, the dependent variable also grows without bound. But in special cases, the dependent variable tends towards a single value. Limits at infinity and horizontal asymptotes help us define that value. What does this all mean? Let's start with a definition and then a demonstration. First, let's talk about a formal definition of a limit at infinity. Let L be a real number. The statement, the limit, as x goes to infinity, f of x equals L means that for each epsilon greater than 0, there exists an m greater than 0 such that the absolute value of f of x minus L is less than epsilon wherever x is greater than m, and the statement, the limit as x goes to negative infinity, f of x equals L, means that for each epsilon greater than 0, there exists an n less than 0 such that the absolute value of f of x minus L is less than epsilon whenever x is less than n. So this is a difficult definition to understand when you're just reading the expressions here. So let's look at a demonstration to help us understand the definition. First, let's suppose that there is a function drawn here in yellow that we believe has a limit L drawn here in light blue. The definition says that the limit at infinity exists if, for any boundary epsilon units above and below the limit, there exists a corresponding m value on the x-axis such that for any value greater than m, the function stays inside the boundary. The smaller the value for epsilon, the further away the corresponding m must be. This is okay because this is a limit at infinity, so we have a lot of space along the x-axis. Horizontal asymptote. The line y equals L is a horizontal asymptote of the graph of f if the limit as x goes to negative infinity of f of x equals L, or the limit as x goes to positive infinity of f of x equals L. Some limits at infinity, if n is a positive rational number and c is any real number, then the limit as x goes to infinity of c over x to the n equals 0, provided that x to the n is defined and x is greater than 0. The same holds true if we go to negative infinity, that c over x to the n also goes to 0. Some rules for finding the horizontal asymptotes of rational functions. So if the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. 2. If the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is the ratio of the two leading coefficients. And number 3, if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is 0. Our first example, what is the horizontal asymptote, if any, of the given function? And so we have a function here. It is 2x squared over 12 minus x squared. Well, these rules for finding the asymptotes of rational functions tell us that we should compare the degree of the numerator and the degree of the denominator. So here, the degree is 2, and here the degree is also 2 because we have the highest exponent is 2 for both of those. So if I go back to this list, it says in number 2, if the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is the ratio of the two leading coefficients. And so our two leading coefficients are going to be 2 and -1. So 2 over -1 gives us -2. So our horizontal asymptote is going to be y equal to -2. Now, if you want to take a look at that and see that it is true, we can go over to Desmos and type in f of x is equal to 2x squared divided by 12 minus x squared. And if we zoom out, we can see, or might as well just put it in there, if we go y equals -2, we can see that the further we pull out, the more that function is going to look like our blue line. So I feel pretty confident in that answer. Next example, evaluate the following limit. So we want to evaluate this limit, but the first thing that we want to do that is we're going to separate this into two fractions. And so I have the limit as x goes to infinity of x over x minus the limit as x goes to infinity of cosine x over x. All right, if I evaluate this first limit, the limit as x goes to infinity of x over x. Well, I can do basically the same thing that I did in the last example. This polynomial has a degree of 1. This polynomial has a degree of 1. X over x is going to give me a limit of just 1. The second limit. Before I can do the second limit, I want to recall something about cosine x. And we want to recall that the values for cosine x go from -1 less than cosine x up to +1. And that's just the values that can come out from the unit circle. Again, let's go back. We're trying to find the limit as x goes to infinity of cosine x over x. All right, so here I'm going to divide by x. So if I go -1 over x is less than or equal to cosine x over x is less than or equal to 1 over x. If I look at these two limits here, the limit as x goes to infinity of -1 over x is going to be equal to the limit as x goes to infinity of +1 over x, because the degree of the numerator is 0, the degree of the denominator is 1, and if we go back to here, if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is 0. And so both of these limits are going to equal to 0. Therefore, the limit as x goes to infinity of cosine x over x has to also equal to 0 by the squeeze theorem. Which we haven't used for a while, but that's okay. And so, since the limit as x goes to infinity of x over x is equal to 1, and the limit as x goes to infinity, I need to draw that in there, of cosine x over x goes to 0, the limit as x goes to infinity of x minus cosine x all over x is equal to 1 minus 0 equal to 1. That is our answer for that one. All right, next example. Evaluate the following limits if possible. So I have a limit here as x goes to infinity of 4x plus 1 over the square root of 3x squared minus 1. I have to do a little bit of manipulation here of this thing because they're not exactly functions that I can write as a rational function. I can't write them as rational functions. So before I get started, I want to make a note. Note that for any x greater than 0, x is equal to the square root of x squared. And so when I go to do this first limit, part A, the limit as x goes to infinity of 4x plus 1 over the square root of 3x squared minus 1, I want to divide the numerator and the denominator by x and the square root of x squared, respectively. So I'll get the limit as x goes to infinity of 4x plus 1 over x all over the square root of 3x squared minus 1 over the square root of x squared. Now I can get away with this because I'm doing the same thing to both the numerator and the denominator. It's the same as multiplying by a funky 1. All right, so I'm going to separate into separate fractions. So here I have the limit. This is equals the limit as x goes to infinity of 4x over x plus 1 over x all over the square root of 3x squared over x squared minus 1 over x squared. And now I'm going to simplify this. And so I'll get the limit as x goes to infinity of 4 plus 1 over x all over the square root of 3 minus 1 over x squared. Okay, so what I'm going to do next is I'm going to take the limit of each term individually. Now, I could write that out and say the limit as x goes to infinity of 4, the limit as x goes to infinity of 1 over x, the limit as x goes to infinity of 3, and then the limit as x goes to infinity of 1 over x. But we can see fairly clearly without going through that it's going to be 4. The limit of 4 is going to be 4. The limit of 1 over x is going to be 0. The limit of square root of 3 is going to be the square root of 3, and then the limit of 1 over x squared is also going to be 0. So this thing is going to end up being 4 over the square root of 3, and we should write that properly and multiply by a funky 1. So we have 4 square root of 3 all over 3. That is going to be our limit. Now, we can use a similar argument can be used for part B, provided that for x that are less than 0, x can be equal to negative square root of x squared. So we got to make that part negative. All right. And so what's going to happen is that all of these values are going to be the same, except that when we get down to this value right here, we will have the limit as x goes to negative infinity, we'll have 4 plus 1 over x all over negative square root of 3 minus 1 over x squared. Now what that's going to do is that's going to give us the same value, except it'll be negative, so we'll have negative 4 square root of 3 all over 3 as our limit for part B. So this is our part A answer, and this is our part B answer. All right, last example. Professor Macaulay colonized a new planet, which he called Macaulay-topia. The graph below represents the population in millions of people as a function of the number of years since colonization began. Use the graph to find and interpret the following limits. First limit says, what is the limit as t goes to 0 from the right-hand side, p of t? Well, that's asking me what happens as I get closer to 0 from the right-hand side. It appears as if it's going to this 60.5. So it appears to be 60.5. And again, the population in millions of people. And so when we colonized, we brought 65 million people. That's a lot of people to move. And then as t goes to infinity, as we go towards infinity, and here we see it's at least to 250, it looks like it's going to this value up here, whatever this is. It looks as if it's approximately between 100 and 150. So we're going to approximate that at 125. And so this new planet's maximum capacity for people looks to be 125 millions of people. Well, that's all I got for today, folks. So, the Star Wars fun fact of the day: the Imperial class Star Destroyer, seen at the beginning of episode 4, A New Hope, is said to be 1,600 meters long. That's over 1.5 kilometers. The newest aircraft carrier produced by the United States of America is the USS Gerald Ford of the Ford class atomic aircraft carrier, and it is only 337 meters long, or just about 1/5 the size of the Imperial class Star Destroyer, which is a pretty big deal. So we still have a lot of room to go and a lot of steel to mine. Well, that's all I got for today, folks. Have a good day.